The next topic we're going to look at is how do we actually visualize these forces we've discussed and how do we analyze them. This is done with what we call free body diagrams. The free body diagrams, they just represent all the forces acting on an object so we can get a clearer picture of how we need to analyze the motion of this object as a result of these forces. So the first thing we should definitely need to understand is the anatomy of a free body diagram. There's two basic components. The first one being that all your objects are going to be represented with a box. If it's a car, a ship, a plane, a soccer ball, any object we ever talk about, we represent it with a box, as there's no need to draw this artistic sketch. A box will very clearly represent your object in a very simple way. The next important concept is that the center of mass would be basically that point. If you imagine a ruler, there's that point where you can place the ruler on one finger where it will balance. It's where all its mass is concentrated. So the center of mass out of an object, if it's symmetrical, will be directly at the center. So we're going to assume for most of the cases we deal with that the center of mass is at the center of the object. So all of our forces will act at the center of mass. So every force we draw on a free body diagram must come from the very center of the object. It's essentially, conceptually, where all force acts on an object. I think the best way is to look at a few examples here so you guys can understand through some practice. So if we take a look at example number 1, what we have is we have a car that is sitting at rest on a roadway. So the first step is to realize, let's represent this car with a box. A nice simple way of not having to redraw this every time. We also know that all these forces will act at the center of mass of this object. So we've now drawn our representative shape of the car, and we have our center of mass. So now we need to ask ourselves, what is actually acting on this object? Well, even if the object is sitting on a roadway, that should tell us that the force of gravity is acting down on it. It certainly has some kind of weight. You would not want to sit under this car, even if it was at rest, because there's a force of gravity that pulls it down. Now, Newton's second law tells us that if a force acts on a mass, which this car has, it will accelerate. So based on this diagram, this car should be accelerating down through the ground. But if any one of us has seen a car on a roadway, we know that not to be true. So there clearly must be some kind of force that acts in the other direction that cancels out this force of gravity. We think back, well, we have a flat surface, we have an object, we're looking for a force that would act opposite of gravity. If you note on this diagram, opposite of gravity would be a force that acts perpendicular to the surface. Hopefully that rings some bells, and you're aware that the normal force from the roadway is what acts opposite of gravity. Now, we generally want to ask ourselves a few questions here. What is the net or the total force in the x direction? What is the total force in the y? And what is the acceleration of this object? Well, if we take a look, there are no x forces. There's nothing pushing or pulling this object forward or backwards. So we have no force in the x direction. Our total force is going to be gravity down, subtract the normal force up, and you should be able to tell, since this is at rest, it's not accelerating. Well, if the acceleration is 0 and F equals ma, well, if a is 0, that means this whole side is 0, which means your net force must be 0. Therefore, your net force in the y is also 0 because there's no acceleration in the y direction. Therefore, you have no net force in any direction, and this object remains at rest. If we take a look at example number 2, we have some kind of mass that's hanging from a rope. So we know forces will act at this center of mass. So we know that gravity will pull this object down. So we will draw our force of gravity. There's nothing pushing this side to side, which is why it's not moving. However, if we look at this diagram, if this is our total net force, this object should accelerate down. If you've ever seen an object hanging from a rope, it does not accelerate down. There must be some force that's acting opposite gravity, equal and opposite. Hopefully you realize at this point that that force must be the force of tension. It's a force that's it's the pull being exerted by a rope or chain or something along those lines, so that must be the force of tension. Once again, in the x direction, I have no forces, so my net force is 0. Since this object is not accelerating, we can go back to F equals ma, the acceleration 0, which makes this side 0, which makes our net force 0. So if it's not accelerating, the net force must once again be 0, therefore our acceleration must be 0. If we take a look at 2 more quick examples, we have a person pushing a crate, and that crate is accelerating in the direction of the push. And if we go ahead and draw our center of mass in on our free body diagram, this one's a little bit more complicated. But once again, we know that the force of gravity is attempting to pull this object down towards the earth. Hopefully we see at this point we have a flat surface. This object is not accelerating up or down, therefore the net force up or down must be 0. So if gravity pulls down, there must be a force that acts up equal and opposite, which hopefully by now we realize would be the normal force. Now if this object is being pushed by this person, that means there's some kind of force acting in this direction. If we think about it, it's not gravity, it's not tension, it's not friction. It must be the applied force. It was being applied to this system by this person. If this object is moving in this direction, nothing is going to be perfect between this crate and the surface. Therefore, you should, or we will have some kind of frictional force. If you notice, however, the force of friction I've drawn is not nearly as large as the applied force. If we take a look, the net force in the x in this case will be the applied force minus the frictional force. And in this case, you'll notice it will be greater than 0, and it will be greater than 0 because we have some kind of acceleration. The mass is accelerating according to Newton's second law. The acceleration is not 0, there's some acceleration, which means we will have some kind of net force in the x direction, as that's the direction of the acceleration. This object is not accelerating in the y, therefore we have no y acceleration, and the acceleration in the y will be non-existent, but the acceleration in the x will be a result of this net force up here, depending on the mass. If we look at our final example, please realize again, center of mass is where our forces act. We have a ball that is rolling on a surface, but it's actually slowing down. Well, once again, we should realize that the force of gravity still pulls this object down. This object is on a flat surface, therefore we must also have normal force acting up. And if you think about it, this object is not accelerating up or down, so these two must be equal in order to have a net force of 0. So we know our net force in the y must be 0 because this object does not accelerate up or down. Now, this object is slowing down. There's nothing pushing it forward. No one is acting on this right now, so there's no applied force. There's nothing pushing it forward. It is slowing down. If you think for a second about what would cause that object to slow down, if you think about it, you should be able to realize that there are imperfections on the ball and there are imperfections on the surface. Therefore, you have some kind of frictional force which acts in the opposite direction of this object. Now, if you take a look, your net force in the x direction will be your force of friction, and there's nothing opposing it. So your net force in the x direction will be the force of friction acting backwards. Therefore, your acceleration in the x direction will be your net force, the force of friction, and you have to account for the mass here. Since it acts in the backwards direction, your acceleration is backwards. If your object is moving forward, but your acceleration is backwards, your object will begin to slow down. You'll be given significantly more practice with this, but just moving forward, start to understand how you would label these forces and how you would determine in which direction and to what degree this object or these objects would be accelerating.